I would like you to think about the constants of nature. Most of these have dimensions, and then their numerical value depends on what system of units you are using. And such numerical values, of course, are not of any general interest. However, one can construct some constants of nature which are dimensionless, and these will have the same numerical value whatever units one uses. They have a numerical value which is thus provided by nature, quite independent of man-made units. One of these numbers is the reciprocal fine structure constant, E squared over cost HC. No, I have it upside down. HC over E squared. And the numerical value, according to experiment, is around 137. And there are several others that one might consider. The next most natural one is the ratio of the mass of the proton to the mass of the electron, mp over me, which has a value somewhere around 1840. One believes that ultimately theory will develop sufficiently for us to be able to calculate these numbers. Up to the present, people have made various attempts in that direction, but they are not convincing, not generally accepted at all. And one must take it that for the time being these numbers are unknown theoretically, but that we may hope that with increasing theoretical knowledge in the future, we shall be able to calculate them. Now there's another one of these dimensionless numbers which I would like to call to your attention. Take the electron and the proton in the hydrogen atom and consider the ratio of the electric force between them to the gravitational force. These forces are both inversely proportional to the square of the distance. Their ratio is a dimensionless number, and this has the value E squared over G mp.me. G is the gravitational constant. Here we have the mass of the proton and the mass of the electron. This number has a value somewhere around 2 times 10 to the 39. It is simply enormous. And the fact that this number is so big means that gravitational forces are extremely weak in atomic theory, and they are quite unimportant. However, this is a dimensionless number which is provided by nature, and we would expect that ultimately some reason will be found for this number, just like we may expect reasons to be found for these other numbers. Now, in the case of these other numbers, we may expect that a theory will be developed ultimately which will enable us to calculate them and get them expressed as 4 pi's and other similar factors close to unity. But how can we ever hope that such a very large number could turn up from a theoretical argument? It seems to me that there is no direct way in which it could turn up, but we may connect it with another large number which is provided by the age of the universe. We take the Big Bang model of the universe, which is now generally accepted. According to this model, the universe started with all the mass concentrated in a very small volume, maybe even at a single point, and there was a tremendous explosion. This matter was broken up into many pieces which flew apart with varying velocities, and of course the bits that were moving fastest soon got farthest away from each other. And the result of an explosion like this is to give you many bodies that are receding from one another with velocities proportional to their distance. Now that is what we observe when we look at the distant objects in the sky. We see that we have many galaxies which are all receding from one another, and their velocities of recession are roughly proportional to their distance. This phenomenon was first observed by Hubble, who made an estimate of the ratio of the distance to the velocity of recession, and that gave an estimate of the age of the universe. Hubble's original estimate was pretty far out because he did not know at all well what were the distances of these distant objects. Improved estimates of this distance give, for the value of the age of the universe, a number which is usually called the epoch, T, somewhere around 18,000 million years. That number is still rather inaccurate because of the uncertainty in the estimates of the distances of very distant objects. But still, there seems to be somewhere in this neighborhood. And here we have another number provided by nature, but this number has dimensions. It is expressed in years. We may, instead of years, use a unit of time provided by atomic theory. Let us take the unit E squared over mass of the electron c cubed. This is a quantity with the dimensions of time, and let us express this age in terms of this unit, and we then get a number somewhere around 7 times 10 to the 39. We get a very large number, as you'd expect for the age of the universe, but it turns out that this very large number is rather close to this very large number which we had before. Now you might say, what a remarkable coincidence. Well, I don't believe that it is a coincidence at all. I believe that there's some reason for this closeness of these two numbers, a reason which we don't know at present, but we may hope to find it out in the future when we have increasing knowledge both of atomic theory and of cosmology. Let us accept that there is a connection between these two numbers, even though we don't know what is the reason for that connection. Well, one of these numbers is not constant. This one is continually increasing as the universe gets older. And if these two numbers are connected, then this one must also be continually increasing as the universe gets older in the same ratio. Well, that is the basis of the argument for the theory which I'm going to present to you. It is just a belief that these two large numbers should be connected, and that therefore this number here should be proportional to T. Now, these quantities here are usually considered as constant, E, G, M, P, M, E. And we see that we have to modify our ideas. One, at least of them, must be varying with the time. Which one varies with the time? That's rather a meaningless question. We can assume that any of them are constant. We can assume that any individual ones are constant, provided the whole ratio is not constant. Talking about whether a thing is constant or not does not have an absolute meaning unless this quantity is dimensionless. And all we can say, which has a definite meaning, is that this dimensionless quantity varies with the time. As a matter of convenience, we may set up a system of units for which the atomic constants are really constant, E, the masses, and then referred to these atomic units, we shall have G varying. So when I talk about G, the gravitational constant, varying, I mean the gravitational constant G referred to atomic units is varying. It would be rather clumsy to bring in these atomic units every time I use that phrase, but it is always to be understood when one says G is varying, G referred to atomic units as varying. It doesn't have any absolute meaning to talk about G varying because G has dimensions, and whether G varies or not depends on the units. So using these atomic units, we find that G varies. G is proportional to t to the minus 1. G dot, the time derivative of G divided by G, is equal to minus 1 over t, minus sign because G is getting smaller, and putting in the value for t given here, we see that G dot over G is equal to somewhere around 6 times 10 to the minus 11 per year with a minus sign. So that according to this theory, G should be varying to this extent here. This variation in G is quite small, and it would be difficult to show it up with terrestrial experiments. Not entirely impossible. Jesse Beams, who is working on this question of the accurate measurement of G, is hoping to improve his apparatus so that he can measure variations of G of this magnitude. It will involve immersing his whole apparatus into a bath of liquid helium and maintaining it for many months in this bath. But he thinks that after a few years he might be able to get a definite result. Now, one would have a better chance of observing this effect by seeing what its astronomical consequences are. In basing this argument on the connection between these two numbers, we are really making use of a more general principle, which I call the large numbers hypothesis. Which asserts that whenever we have a very large dimensionless number turning up in nature, that number is to be connected with the age of the universe by the appropriate formula. Now, we have to face the question of how we can bring in the variation of G into physical theory. Many people who have worked on this problem have followed a very primitive idea of gravitation, in which they suppose that gravitational mass and inertial mass are two different things which can vary independently, and if you allow one of them to vary with respect to the other, you do get a theory with the variation of G. But I find that kind of argument quite unacceptable, because it goes right against the whole basis of Einstein's theory, which is that gravitational mass and inertial mass are the same thing. You must have them both the same thing if you are to explain gravitation in terms of the curvature of space. Now, the Einstein theory of gravitation is so successful that we can't just throw it overboard and go over to a pre-Einstein theory like these people do who work with different gravitational and inertial masses. So I propose that one should deal with this in a different way. We have to retain the successes of the Einstein theory, because it is so successful in explaining the motion of the perihelion of Mercury, deflection of light passing by the sun, and other things. If we are to retain these successes, how can we have G varying? Well, we must remember that G varying means G referred to atomic units is varying. And it may be that the atomic units are varying with respect to the units that one ought to use for the Einstein theory to be valid. So I propose that there are two systems of units which are important in physics. This idea of the two systems of units was first introduced by Newton before the war. And I should call it Newton's hypothesis. According to this hypothesis, there's one system of units which one should make use of when one is using equations of motion. The equations of motion, whether they are the original Newtonian equations of motion or the Einstein modification, are valid only referred to this system of units, which Newton called mechanical units. Then we have the atomic units, a unit of time provided by atomic clocks, a unit of distance provided by the spacing of crystal lattices, and that is the second system of units, which is not the same as the mechanical units. We may assume that the velocity of light is equal to 1 with both systems of units. That's the obvious thing to do, and that means that the ratio of the two units of distance is the same as the ratio of the two units of time. The unit of distance and the unit of time are both changed in the same ratio when we go from one of these systems of units to the other. By adopting Newton's hypothesis, we are able to secure that G, referred to atomic units, varies with the time, and also to retain the successes of the Einstein theory. In the Einstein theory, we have an element of distance or time related to two neighboring points, which appears as the ds in the equations of the Einstein theory. And if this ds is measured in mechanical units, so that the Einstein equations hold, I shall write a dSE. Then the same ds measured in atomic units, I shall write dSA. We have these two quantities referring to the element of distance or time between neighboring points, dSE, dSA, which just give this element referred to the two systems of units. Well, now I want to develop the theory based on the large numbers hypothesis and the Milne's hypothesis. I should say perhaps that I feel very strongly that this large numbers hypothesis is correct. I'm not so sure about Milne's hypothesis. I would be quite happy if someone could propose a different idea for allowing G to vary without disturbing the successes of the Einstein theory. So far no one has come up with such an idea, so that we must stick to Milne's hypothesis. There is another application of the large numbers hypothesis which we have to make. Let us consider the total mass of the universe and express that in units of the proton mass, so that we may say we take the total number of nucleons in the universe. This will be a very large number. It might be infinite, of course, if we adopt a model of the universe which is infinite. Now, I don't want to restrict myself to a particular model of the universe, finite or infinite. In the case of the infinite universe, there is another quantity which we can use instead of the total mass, namely the mass of that part of the universe which is receding from us with a velocity less than a half the velocity of light. I take a half as just some definite figure, but any similar fraction, a third or 3/4 would do as well. Taking the amount of matter which is close to us, according to some arbitrary formula like that, will give us a large number which can replace the total mass of the universe when the total mass is infinite. Now, this total mass is something which one can estimate fairly well for the case of that matter which can be observed, the matter which is shining and which we see in the form of galaxies and stars. There might be a good deal of matter which is unobservable in the form of black holes, dark stars, or even intergalactic gas. One can make estimates of how much of this invisible matter there is. It could hardly be extremely large, or its gravitational effects would show up. If we make reasonable assumptions about the amount of the invisible matter, we come up with a figure for the total mass expressed in proton masses, somewhere of the order 10 to the 78. There's quite a lot of uncertainty in that figure, some powers of 10, but anyway, it is somewhere of this order, and from the large numbers hypothesis, we should expect that it varies in proportion to t squared. So the large numbers hypothesis leads us to expect that the total number of protons and neutrons in the universe is not constant, but is increasing proportionally to the square of the epoch. That means there must be continuous creation of matter. this continuous creation must be some new physical process, not connected with any of the processes observed in the laboratory. It's a cosmological process. It is a very small, when you just consider a small interval of time like a year, so it could hardly show up with direct observation. But still, if we are to follow through our assumptions consistently, we must assume continuous creation of matter. There have been other cosmological theories in which people have postulated continuous creation of matter. The steady state theory, which several people have worked on, but the theory that I'm proposing to you now is, of course, essentially different from the steady state theory, because we have G varying. With a steady state theory, G would have to be constant. Everything has to be constant. So that this theory is not to be confused with the steady state theory, even though in both cases there is continuous creation of matter. I simply want to follow out in a logical way the consequences of the large numbers hypothesis and Milne's hypothesis. You see that we are led to postulate continuous creation of matter, continuous creation of protons and neutrons. And then the question arises, where is this matter created? There are two reasonable assumptions that one might make. First assumption is that this new matter is created uniformly throughout the whole of space. In that case, most of it will be created in the intergalactic space, which forms by far the majority of all the space. This assumption I call the assumption of additive creation. New matter is continually being added to space, sort of radioactive process which can occur in the vacuum and which generates this new matter, of course violating conservation of mass. You might say, is it justified to violate conservation of mass? Well, conservation of mass is not an absolute law, because mass is something with dimensions, and whether mass is conserved or not depends on the dimensions that you use for measuring the mass. And if we measure the mass in proton units, then we have non-conservation of mass. But if we measure the mass in terms of a unit which refers to the total mass of the universe, then we would have conservation refer to that unit. Well, the other assumption that one might make with regard to the creation of this new matter is that the matter is created where it already exists in proportion to the amount that is existing there. In that case, every astronomical body will have its protons and neutrons multiplying up. The new matter is continually being created where it already exists. Each atom has a chance of creating new atoms in its close neighborhood. I call this multiplicative creation. Presumably the new matter will be created in the form of atoms of the same nature as the atoms already existing there. So we have these two possibilities, that the creation may occur just as a sort of additive process applying to the vacuum, or the matter which is already existing may be multiplying up. I don't know which of those two processes to observe, to prefer. For the time being, one must keep them both in mind and see which of them leads to the more reasonable consequences. We are now in a position to be able to calculate the ratio of these two ds's which we have according to Newton's hypothesis. Let us consider the motion of the Earth around the Sun. This very simple example. Use the Newtonian formalism, which is good enough. Then we have a formula something like this. G times the mass of the Sun is equal to, well, I use capital M for the mass of the Sun, is equal to V squared R. V being the velocity of the Earth in its orbit, R the radius of the Earth's orbit. That's the elementary formula from Newton's laws. Now, this formula must apply whatever units we use. We might use the mechanical units. In the mechanical units, every quantity occurring in this formula is a constant. Referred to atomic units, the Earth moves steadily in this circle around the Sun with constant velocity, constant radius. Now, if we apply the formula to atomic units, we shall have the quantities referred to here varying. Let us call them Ga, Ma equals Va squared Ra. The suffix A denotes the quantity measured in atomic units. How do these quantities vary with the time? Ga, we have already seen, varies according to T to the power of minus 1. Ma, that is the mass of the Sun, referred to proton as the unit of mass, or if you like, the number of protons or the number of neutrons in the Sun. Well, with additive creation, this number will remain constant. The new matter which is created will be far away in the intergalactic space and won't affect the mass of the Sun. So Ma is proportional to 1 with additive creation, but with multiplicative creation, Ma is increasing proportional to T squared. Every bit of matter is multiplying up, so that we have Ma proportional to T squared with multiplicative creation. Now, let's go on to Va. Va is the velocity of the Earth in its orbit. This we can express as a certain fraction of the velocity of light. It is dimensionless. It thus has the same value, whether we use atomic units or mechanical units, and this Va cannot vary with the time. Va is proportional to 1 in both cases. Then we can use the formula to calculate how Ra varies with the time. Ra is proportional to T to the minus 1 with additive creation, and is proportional to T with multiplicative creation. Now, what does this mean? If we assume additive creation, the distance of the Earth from the Sun, measured in atomic units, is getting less. The Earth is approaching the Sun. All the distances in the solar system will be contracting in the same ratio. This is a new cosmological effect to be superposed on all the effects arising from known physical causes. the whole solar system is to be pictured as contracting when we measure the distances in atomic units. On the other hand, if we assume multiplicative creation, we have all distances in the solar system expanding. The whole solar system is expanding, and that again is a cosmological effect to be superposed on any effects arising from known physical causes. There we have the possibility of making observations to check this theory. We just have to take some distance provided by the solar system, observe it accurately, make the observation with respect to atomic units, and see whether this distance is increasing or decreasing. If this whole theory is wrong, the distance would be constant, of course. But if we do find a change, then we can distinguish between the two kinds of multiplication of matter. That is a question which a good many people are interested in nowadays. How would one apply it in practice? Let us first of all take the case of the moon. We may apply this formalism to the moon in its motion around the Earth. And we find that with additive creation, the moon should be approaching the Earth at the rate of about 2 centimeters a year. With multiplicative creation, it should be moving away from the Earth 2 centimeters a year. It would just be necessary, therefore, to observe the moon's distance with great accuracy, allow for all the disturbances coming from other known physical causes, and see whether there is a residual motion which has to be interpreted as a cosmological effect. And then from the sign of this motion we can check the theory and distinguish between the two kinds of creation. But people can observe the moon's distance with great accuracy at the present time because lasers have been put on the moon by astronauts, and people are shining laser reflectors. Reflectors have been put on the moon by the astronauts, and people have been shining laser light onto these reflectors and observing scattered light, reflected light coming to Earth. This reflected light is extremely weak, but still it can be observed. And in that way one can get an accurate observation of the moon's distance. The frequency of the laser light, or the wavelength, is determined by atomic dimensions, so that we are getting the moon's distance referred to atomic units. I've heard that people have been able to measure the moon's distance with an accuracy of 6 centimeters, and that is continually being improved. It's not yet quite good enough to observe an effect of 2 centimeters a year, but still it is not so far off. However, in the case of the moon's distance, there is a lot of trouble arising from perturbations caused by the tides. There are people in Canberra whom I talked with, who are making a study of the effect of tidal action on the solid part of the Earth's surface. It seems that there are up and down motions even of the solid part of the Earth's surface of, say, tens of centimeters per year, per day, which they can observe. They hope to be able to get accurate observations of these up and down motions caused by tides, and they hope in a few years to be able to get the moon's distance with the necessary accuracy to check on these theories. Well, these observations of the moon's distance are very complex because of the effect of the tides. And you might think, why not use some other observations where tidal effects don't matter? You could do that by observing the moon's motion in the sky, the moon's angular velocity in the sky, and getting the angular acceleration by seeing how it varies with time. The moon's position in the sky can be observed with very great accuracy by observing the occultations when the moon passes in front of a star. People have been observing the moon's motion in the sky for centuries, but they have, during that time, referred their results to what they call ephemeris time, time as marked out by the motion of the Earth around the Sun or the motion of other planets. Ephemeris time is, of course, the same as the time measured in the mechanical units of miln, the time for which the equations of motion are valid. However, since 1955, people have been observing occultations of the moon with atomic clocks, and those observations give information about the moon's motion referred to atomic time. Let us consider the difference of the two observations referred to ephemeris time and atomic time. People use the symbol n to denote the moon's angular velocity. N dot over n is the moon's, gives the moon's angular acceleration. Let us define n dot over n difference to be the atomic value of n dot over n, this thing observed with atomic time, minus n dot over n, referred to ephemeris time. People have been studying this difference, in particular a man called Van Flandern, working in Washington at the Naval Observatory there, and from a lot of calculations that he's done, he got a figure for this difference, n dot over n atomic minus n dot over n ephemeris, amounting to plus or minus 5 times 10 to the minus 13. 10 to the minus 13, 10 to the minus 10 per year. With a minus sign in front. Here, the effect of the tides doesn't matter because it's going to affect both of these in the same way. We're just taking the difference of these two time scales. Van Flandern worked out the effect of his observations on the theory with G varying, but he used the primitive theory, which I referred to first, and which I don't think is a very good theory. I I think it's quite unacceptable. According to this primitive theory, G dot over G is equal to a half n dot over n difference. And that would be sorry, I gave the wrong figure here. I should have given the figure 16 plus or minus 10 for the difference of these two accelerations. And then G dot over G, as worked out by Van Flandern with this primitive theory, gives you minus 8 plus or minus 5 times 10 to the minus 10 per year. And Van Flandern was rather happy with that result because he said that this supported the theory. Of course, I don't think one should accept this figure of Van Flandern because it does involve this primitive theory which would completely destroy all the successes of the Einstein theory. One should instead work with Milne's hypothesis, and then one gets this result, Milne, with additive creation, G dot over G equals minus n dot over n difference. Or Milne with multiplicative creation would give G dot over G equals plus n dot over n difference. It's just the change in sign according to whether we have additive or multiplicative creation. Now with additive creation we would have here 16 plus or minus 10 times 10 to the minus 10 per year, and with multiplicative creation 16 plus or minus 10 times 10 to the minus 10 with a minus sign per year. It means that working things out with Milne's hypothesis and using multiplicative creation, we get an effect rather larger than what the theory requires. We must evidently take multiplicative creation. Additive creation would give the wrong sign. So Van Flander's observations support multiplicative creation and give rather too large an effect. One need not be very much disturbed by the effect being too large, because there are a lot of inaccuracies in these calculations. The inaccuracies come from the fact that we have to study the motion of the moon. It's moving in the field of the Earth and of the Sun. It's the three-body problem, which in any case is a very complicated problem to use, and people find that it's better to make direct use of computer calculations instead of referring to the old instead of referring to the old theories of the three-body problem. But there are also the other planets in the solar system, and they produce effects which cannot altogether be neglected. People working on these calculations usually make assumptions that a good many of the effects of the other planets can be neglected. And then they look more closely and they see that some of these effects which they were neglecting cannot be neglected, and they have to revise their calculations. Van Flandern has been revising his calculations, and This was the figure he gave in his published work, and his revised figure is somewhat smaller than that. But still, I think we must give them more time to look into their calculations more closely and make a greater search for possible errors. The net result then is that Van Flandern does give some evidence in favor of this theory with multiplicative creation. We ought to wait a little while for confirmation and a chance to see how accurate these results really are. Another method that one might use in order to check on this theory is to work not with the moon at all, but with one of the other planets, such as Venus. Shapiro has been working for some time with radar observations of the planets. You send radio waves to a planet and observe the reflected waves. One can get an effect that one can observe using the big dish in Arecibo. We're waiting for Shapiro to give us some definite results. He's rather hesitant about committing himself. I heard recently from his assistant that his results do rather support additive creation, but I haven't been able to get any definite figures from him. Well, that is the situation at the present time. It's just a little bit too early to answer the question, does the gravitational constant vary? But in a few years' time, it seems likely that we shall have a definite answer to it. If we do get evidence that the gravitational constant is varying, that will set physicists wondering whether maybe some of the other constants are also varying. I started off with these constants, 137 and 1840. Now, from the large numbers hypothesis, we couldn't have numbers of that size varying with some power of t, but they could vary logarithmically with t, and that would be quite within the spirit of the large numbers hypothesis, to have one of these numbers varying logarithmically with t. Well, there is evidence that this number does not vary at all. Evidence that comes from spectral observations of the very distant galaxies. It seems pretty certain that this one is a constant. Does this one vary? Well, no one has worked on that problem at all. And it seems to me that it is a most interesting problem. Could there be a logarithmic variation with time in the ratio of the masses? It would be quite feasible to check on this experimentally with the existing apparatus, because one has very accurate atomic clocks nowadays, and some of these atomic clocks involve an oscillation of an electron in the cesium atom, for instance, and some of the atomic clocks involve the oscillation of some atomic nucleus, like in the ammonia clock or the methane clock. Now, one could compare the timekeeping of the cesium clock with an ammonia clock, for instance, and see how accurately they keep together. If there is a variation of this ratio of the masses, then these two clocks would not keep accurately in time. I've been told by the people who work with these clocks that they can do their timekeeping with an accuracy of 1 part in 10 to the 13. Now, if there is a logarithmic variation, it would of course be much smaller than the t to the minus 1 variation which we have here, smaller by a factor 100 or so, but even so it will still be of the order 10 to the minus 12. One would expect the timekeeping of the two clocks to show a discrepancy of 1 part in 10 to the 12 per year, and that is within the range of the present accuracy. I hope someone will do that experiment. I feel it's well worthwhile because this ratio is such a mysterious number, and no one really knows what it can come from. And the first step in that direction will be to see whether it is really a constant or whether it does vary with the epoch. I might finally refer to another possible application of the large numbers hypothesis. There is another large number which has turned up in recent astronomical work, not so large as the others, but still fairly large, and one might expect the large numbers hypothesis to apply to it. This is provided by the microwave radiation. This radiation of microwaves, which is falling on the Earth uniformly, coming from all directions and at all times. And it is observed to correspond to black body radiation of a temperature around 2.8 degrees Kelvin. People assume that this radiation is the remains of an original fireball. At some early stage in the universe, there was radiation at a high temperature coupled with matter, and during the course of the evolution there was a decoupling between the radiation and the matter. After that, the radiation just cooled owing to the expansion of the universe. Now, if you have black body radiation and you let it cool according to the uniform expansion of the Big Bang hypothesis, it remains black body radiation, but its temperature falls, and the temperature T falls in proportion to the reciprocal of the epoch. According to this hypothesis of the primitive fireball, this 2.8 degrees Kelvin radiation is what is left of that primitive fireball after it has cooled for a long time in accordance with this law of cooling, which follows from the expansion of the universe. Now, this argument is not really acceptable if one believes in the large numbers hypothesis, because from this 2.8 degrees we can construct a dimensionless number. Let us form kT. This is the temperature of the microwave radiation. Let us form kT. That gives us an energy, the energy of a photon in the central part of this radiation. And let's just express this photon energy in terms of the rest energy of an electron, MEC squared. There is a dimensionless number. And that turns out to be of the order of 5 times 10 to the minus 10. It's not such a large number as we were discussing previously, 10 to the 39, but still one might suppose that this is really some number of cosmological significance, and that it should vary with epoch, probably in proportion to t to the minus a quarter. From the size of this number, one would think that it should vary according to the law t to the minus a quarter. Of course, I've used the mass of the electron here. I might have used the mass of the proton instead. And then I would have got something smaller, something of the order 10 to the minus 13, proportionate to t to the minus a third. The theory is not good enough to distinguish between t to the minus a quarter and t to the minus a third. But in any case, it would seem that we have here a number which is getting smaller according to a different law from this t to the minus 1 law of the primitive fireball. It seems in that way that the primitive fireball idea is not consistent with the large numbers hypothesis. And if the large numbers hypothesis is to be accepted, one must suppose that there is some factor coming in which causes this microwave radiation to cool more slowly. That factor could only be some intergalactic matter. There might be intergalactic matter, for instance, ionized hydrogen, and the radiation would interact with the free electrons and would exchange energy with them, and then the cooling would be according to a different law, and it could very well be according to a law such as this. The amount of intergalactic gas would have to be sufficiently small so as not to disturb observations of the most distant matter which can be seen with visual and radio telescopes. But even so, it is quite permissible to fix a density for the intergalactic gas which will be adequate for this purpose and still too tenuous to be observed by direct astronomical means. I will stop there. You can, yes. Energy and mass are rather interchangeable concepts, yes. No. I should say that this theory does not apply to the very early history. We are considering how these dimensionless numbers vary with the time, but the arguments that we have been using apply only to the asymptotic form of this variation for large values of t. And when you take values of t which get much smaller than 10 to the 39, the theory tells you nothing at all. ratio of a photon. Yes. Yes. That would be possible, yes. That would be quite reasonable to do that, and that would change the result by a factor of 1,000. But that affects the later argument very much. That will not be affected, because in any case the argument applies only asymptotically for large values of t. You can't get away from that. If you have, suppose you have a number, some dimensionless number k, which really varies according to the law c1 e to the power of alpha 1t plus c2 e to the alpha 2t with alpha 1 greater than alpha 2, then it is only the, I shouldn't say the c1 t to the alpha 1 plus c2 t to the alpha 2. Then for large values of t, we have just one term dominating in this formula, and the whole argument applies only to the dominant term, and it doesn't tell you which in this case is the first term, and the argument doesn't tell you anything about this second term here. This second term here could be very important for the early stages of the universe. I don't hear very well what you say. No, the invariance of G is not deduced in deducing T. It is just follows from Hubble's constant. The volume would increase in proportion to the cube of the age, I think, if you have the particles moving with constant velocity apart. You mean this one? No, I have no theory at all about this. I would like to get these first terms in order.
My own observations over a number of years as to the pull of gravity on my body when I managed to confirm the additive theory. I think we all owe a great vote of thanks to Professor Dirac. Some of you who were here Wednesday night know that he gave us a superb lecture under very trying conditions, and the conditions which would have produced many another lecture through the shaking mass of jelly. And so, without further ado, I think we all must express our appreciation